of the Fortran training was about introduction to the modern Fortran and the vector syntax and such. The second one was about object orientation in Fortran, that you can actually use all the tricks in the book that you learn from object-oriented programming. And the third one was automatic offloading to the GPUs by using standard ISO Fortran. And the last one is integration of Python and Fortran. So while Python is nice language, it's so-called high productivity language, easy to learn, easy to use, easy almost everything, and it's also very, very powerful. But it's not a high performance language. It's not really made for doing numerical calculations. Those of you who do numerical calculations in Python are generally relying on libraries. Those libraries are either written in C or Fortran, those old ancient languages that are tailor-made or can be tailor-made to give you the peak performance that you expect. So every time you call up something from NumPy or something like matrix multiplication, which will be repeated to the extent of being boring today, and then deep behind the scenes are either a C routine or Fortran routine that actually do the performing the calculations. So, but you are in the unfortunate situation that there isn't a library for everything. And when there isn't a library, then you have to write the Python code, and the speed between Python and normal, if you just write normal Python, and Fortran can be 100 times or more. So it's important that if to write time-consuming part of your code in Fortran, and you can just call up that code and do all the housekeeping, the admin, the stuff that are best handled in Python, you handle in Python. And the things that require high-speed computation, you just call up a Fortran routine, which of course require an interface between the two languages and somewhat, not really deeper knowledge, but some knowledge about data types, which we covered so if you're unfamiliar with the different data types and how important it is, and the different way of specifying data types, please review day one, and where I go at some length to display or show and explain how the different data types are, because let's say, for instance, in C, you have two data types for floating. You have float and you have double. You have no idea what that actually means, except that people tend that double precision must be better than float. Yes. But since Fortran is a bit more strict about knowing types, then the types that you use in Fortran can be stated in human form, which means that how many decimals do I actually need, and what kind of range to the exponent do I need. And you say maybe you need 14, 15 decimal places, and at least 100 plus minus on the exponent. You feed that in, and Fortran's runtime system or compilers will give you a data type that fit with a handle, a number. It gives you a number back, but that number could be totally arbitrary. Some compilers use 8 for 8-byte variables, but that's up to the vendor to decide, so never rely on that number. That's also covered. And it's also in Python are also fairly strict on this. Python also specified how many bits and so on a variable should be. So this is also important to know that you are using the correct variables. It's not very hard. I mean, it's fairly easy. So that's a little bit of introduction. I say the introduction to modern Fortran. This is the same slide I've used for all the trainings. that we expect that you have some programming expertise before. And Fortran is old, but C is also old. For those people who are born in this millennium, they don't see the difference from 1954 and 1972. They are both decades before they were born, so they don't see that there is many years between them. For me, in 1954, it was before I was born, so it's ancient. But 1972, I can remember. So I don't think C is old, but I do think Fortran is old. So it's a matter of perspective. But at that time in 1954, they were using punch cards, as you see them here. Each one punch card, each one line. So programming in these days were very, very different than today. But Fortran stands for formula translation. It's tailor-written to express mathematical formulas to be calculated. So it's, as somebody said at a supercomputer conference I just returned to in Hamburg, Fortran is surprisingly efficient. So, and yes, it is. It's a language tailor-made to do numerical operations. To do strings in Fortran, don't really think about it. That's much better done in Python. Python, you can write it in one line. Fortran will take you the rest of the day to figure out what to do. So don't do that. Some versions, and we are now up to 2018, which is the latest one, but not all vendors have implemented all the standards in 2018. And we are also now on the verge of seeing Fortran 2023, which introduces a few more interesting stuff. But I have made a copy of the standard if you are interested to read, but it's a hard read to read them the standard. So you just watch the examples, and I try to cover some of the more modern things and so on. So there are a few things that happened in the 2008 and the 2018 standard. So that's I've touched upon in the former trainings. So I had to dig up about Python. Python first released in 1991 as Python 0.90. People claim that Python is earlier, yes, and there existed Python even before that and some other languages. But it's a high productivity language, which is the important thing here. So it's easy to learn, easy to program, and you can do it interactively, or you can do it batch-wise. You can use Jupyter notebooks and so on. So it's a very versatile language, and it's widely used. So it is a good language to admin numerical calculations. Just do the hard work in some C or Fortran routines. So you could have the best of the two worlds. So there are little theory to present today. I assume that you are familiar in both Python and Fortran. The number formats are identical. Both use internal representation of the different types, which is IEEE 754. That is a standard that specifies the width. And that, first of all, it specifies the width of how many bits and bytes each numerical number contain, but it also specifies how the bits are organized. In the older days, they were like the VAX 780 type system. They have two data types of called double. They had slightly different number of decimals and widely different exponent. You had one of them had an exponent only plus and minus 38, which it's on the verge of being able to keep Planck's constant. So, but today it's all specified for the x86 and also for the ARM processors and RISC-V and so on. So the one and Power and so on, the one that you will get to use, they have all IEEE 754. So that part is safe. And there are single and double. And there are also 32-bit integers, 64-bit integers, and of course there are 8-bit integers and a byte integer and 2-byte integers and so on. So all of those can be specified. But the standards for the hash precision and the floating point, 1-byte floating point, isn't really implemented in all the processor yet. But since we are talking Fortran, of course, Fortran also have complex data types installed. You have the one that using single precision variables. They have 2 of them since a complex number contains 2 numbers. I am a bit reluctant to call them a vector because there's a distinct difference between complex number and a 2D vector. So we'll call them complex numbers. So they contain 64-bit. And if you are using the numbers to do 2 numbers in double 64-bit, they are in total 128, which is important when you are going to specify floating point complex variables in Python. So that gives us the opportunity to go straight to the exercises because there is not much more theory to convey. So I have already requested an interactive node. So you have the choice now of just following me, or you could type along as we are progressing. So I can give you a minute or so to do the reservation. I think you should have the reservation in the README file. So it's here. Here is the reservation you can copy out, which I have already done up here. Or here is my actual command. I requested 5 hours and 4. I have requested 2 nodes, and I recall there should be enough for many of you to ask for 4 tasks. That gives us some leverage when we want to do threading. So assuming that some of you have managed to get in, we can go on with the exercises. So we have now established ask ourselves for a compute node, an interactive compute node. We need to purge all modules that we'll have. That shouldn't be that hard because I didn't put anything in. Then there's a nice trick to be played. The people that running Saga has been so kind that to make a SciPy bundle for us. The SciPy bundle contains NumPy and SciPy and Python. So if we launch that module, we'll have a lot of things. So no questions. We go here. Yeah. We'll have a lot of things like Python. And since in the modern day, you don't really need how to specify Python 3 that you had to do in the old days, but we have Python 3.310, which is a fairly new Python. So the other thing we need to check is that we need to have a mapping between Python and C. C is also used as an intermediate thing here, not only Fortran. So they are the people that are doing the interface. They have a lot of interesting things going on behind the scenes that we don't really need to care about. But this one we actually need. And This is because we are using the standard ISO environment for Fortran. And from there, we are calling the real 32 to specify a real number, float number, 32-bit long. And that correspond to the float in C. So here is a link between a 32-bit number, single precision, to a single precision equivalent in C. So the real 64, same thing, that correspond to the double in C. I also used real 32 complex float and real 64 complex double. Complex float is C, but C doesn't really have complex numbers built in per se, so this is the way it's normally done. Then we are assuming that, or normally in C, an integer int is 4 bytes long, 32-bit, but not always, because on the x86 computers that we normally know, this is true. But if you write C code for other processors, and especially smaller processors, this one could be quite interesting. So if you are in doubt, check out the size of your int and size of your long, because in C, a long is not always 64-bit. In general, the rule of thumb is that a long could keep an address. So for x86 with 64-bit processor, this is easy, this is 64-bit. But for other types of system, a long might not be 8 bytes. So instead of just using long, you can use the more verbose way of dealing with C. But now we are over in C programming, which this training is not about. So, but I just want to stress that the data types can be important, because the size of the integers can be quite can be dangerous, because what is 127 plus 1? Most of the time it should be 128, but if you overflow, it could be -1. So, and there's a distinct difference between 128 and -1. So overflowing can cause all sorts of havoc, and in the first training I had about accident, well, a lot of people were killed because of a floating point, of integer overflow. So this file I have here need to be copied to .f to pi f to c map. So if I take a list all the files, also the hidden ones, I will see that I have now, I have already done this. I have a file called f2c, which contains this dictionary containing the mapping from Fortran to C. Okay. README. So what do we do more? We will start by making a Python module. And we have a Fortran code called primes. This is some code I got from somewhere else. It's a prime number, implicit non-integer in, out. Here I just rely that the integer are 4 byte, and the logical could be anything, but normally they are 4 byte. And declare an integer, prime is true, and so on. And we check until the square root and so on. And then we set the prime numbers. So this is just a Fortran program that gives you a subroutine that gives you the prime numbers up until the n. So README again. So we now issue this magical command. Yeah, you see, this is the magic. This is a built-in command, and we can see the usage to construct the extension, da, da, da. So if you don't type in any, give it any arguments, it will print out this usage. And this usage is almost like the man page. Normally usage will be much simpler, but we are now lucky. It will give us a lot of options. So nice to know. If you are looking for something special, just issue the name and it will print out the information. So we now use the C and the M, and M is for the module that you can import is given by the M. We'll see if this works. It doesn't say anything that it didn't work. There's a lot of strange things, and especially this red one, but we don't have the ARM F language installed, so it's no big deal. You see it's starting here. It's running config cc. You see there's a lot of C things going on here. It mapped our mappings to the Fortran kind, to the C kind, and reading the Fortran code and doing a lot of looking for compilers and such. And at the end, it will call up gfortran here and here a couple of times, and then it will issue this line. The important thing here is that the -O is the name of the, normally it will be name of the executable since O is the output, but since we are not going to make an standalone executable, we are making a shared library. So the output is the name of the shared library. A shared library is like almost like an executable, but it doesn't contain any main. So if we are running the famous command LDD to see what that calls up, we'll see that this prime rely on some underlying more libraries. Fortran, of course, the mathematical library, the GCC library, the QuadMat, it's multiple precision mathematical library. But there are no missing libraries here. All of them are resolved. So that's good. What else will we expect? Then now we can just cat go. Now we can actually launch the primes.py, which is very simple. Import primes, C array, 100 numbers. So it's a very small Python program. Print out the prime number up to 100, between 0 and 100. And that wasn't too hard. So now we manage to call Fortran from Python for the first time. Any questions to this? I don't see any questions on the collaborative document, but feel free to interrupt if you have questions. or you want time to do this yourself? Or should we just continue with the next? We have some examples, and we should have ample time for you to actually do this yourself while I'm talking.
May I ask a question, Ole?
Yeah, please go ahead.
I was doing this exercise. So my question is, usually there might be some kind of very heavy computing subroutines in Fortran that is very difficult to do it in Python at the expected performance level. So
Yes.
this is an example that where we can do the such use case, right?
Yes. So we will cover in the later demos things that are impossible to do, because if we started the large matrix multiplication in Python, we could probably get the answer to the next training session in a year's time. So, because that's how slow Python is to do numerics inside Python. So, was that more in line what you wanted to know?
Yeah, and also I want to know whether you have, do you know if what is the statistics of this specific routine, and that do you think many people are using this or it's quite new?
I'm not sure how many people actually are calling. Well, I can say that almost all users, everybody who use NumPy are calling Fortran from Python or C from Python. I haven't covered C because this is not a training event in C. So everybody who are using NumPy are using Fortran routines deep down hidden away in some library. So the point is that if there is a library, it's normally very, very optimized and performs excellent. But if you don't have a library, you are in a bad spot. And since there are hundreds of thousands of code in the scientific programs I've seen, there must be a reason for that you cannot have libraries for everything. So all those codes that you have to read between all the library calls that actually do, especially weather forecast codes, or many other codes, everything that operates in 3 dimensions have 3 nested do loops outside of each other, scanning through a data structure. And of course, that's very, very time consuming in Python. Fortran is constructed exactly to do this in the best possible way. So the performance is far higher. So yes, everybody is calling Python. It's calling Fortran from Python, unaware that what they are doing, because NumPy hides everything away for you. So if you didn't know that the primes module was a Fortran module, you wouldn't know. You would just call the prime and be happy, which is one of the things that it's a beauty with Python.
Yeah, thanks. Please go ahead.
Yeah, maybe somebody want to, if you want more time to try this out yourself, just shout out either on the document or unmute yourself
And ask questions.
and ask questions. It's an interesting question, but we are fortunate enough that all the data types that we are using are IEEE 754. So there are no conversion from Python int to Fortran int or C int. They are exactly the same. So there's only a typing thing so the compiler can understand what we are meaning. So They are only labels. So there is no conversion between integer, and they are, everything that we use is just references to memory cells containing these data types. So there are no conversion. The only overhead there is a function call, and function calls are generally fairly well optimized and doesn't take that much time. So yeah, so in that respect we are lucky. So that's the focus on the importance of having a common data type for all languages. This has been since the early days of x86 systems, has been that C and Fortran played very well together because the common data types. If you were to convert data types from one type to another, it will be a nightmare, because converting floating point number from one type to another type is very, very hard. Not very hard, but I think I had time for an anecdote. Many years ago, we had at the Institute of Chemistry, we had a system with the MIPS processors. That was before IEEE 754. And we had a common super mini that was a convex system. And some bright guy had a Fortran file that he had written unformatted. That means bit by bit to a file, so that the digital representation of the bits on the convex was written to a file, and he wanted that large data file to be read on the MIPS machine, which of course had a different floating point format. So I was faced with the task of converting this binary file with data types from convex to data types on MIPS, which are totally different. So I was thinking for it some time, and then I asked some people. And so I'm not claiming that I figured this out myself. I got help. And this is exactly almost like what Alexander the Great did when he couldn't untie the knot. He just drew his sword and cut it in half, thereby unlocking the knot. The trick I was told to do was to write a Fortran program called read. It would open, just to tell you the complexity, it will open the binary file unformatted. It will print out on standard error in ASCII format with enough decimals to be sure that you have all the precision to the screen. Then I will write a Fortran program reading from the keyboard and then writing unformatted to a file. Then I launched a remote shell at that time, not SSH, but RSH, a remote shell with the read command, piped the output into the write command and let it run overnight. So when I arrived in the morning, I suddenly had all the numbers converted. So this is a story of how to make it simple. So I could simply convert them over to ASCII printable format and back. If you want to do it normal way would of course be to figure out how the bits and bytes were done internally and have a converting routine in C that could take each individual bit. But that required fair amount of work. This was very easy to do. So it's an interesting question. But we are lucky that some people have actually got their acts together and agreed on a formal standard for the floating point numbers. But in these machine learning times, it's still debatable what floating point 16 is. There are brain float and there are FP16, and there is also an 8-bit floating point. So then, but they are not part of the IEEE 754 yet. So I wonder what's going to happen if they're going to be two 16-bit formats and one 8-bit, or what's going to happen. So it's just wait and see. So anecdotes can be nice for some time. We have I don't need this one, RM. I haven't cleaned this one because this is my directory. This is not what you'll see in your directory that you copy. So the map is there. This is important. If that's not there, it will fail. So what's in the README? Of course, we have make sure it's present, and of course the module is already mounted, loaded. So we go straight at it. This time I introduced an F90 directory to keep the Fortran files in the own structure. You see here, just setting up the interface variables here is far more than the actual thing. This is the beauty of modern Fortran. This is exactly what I'm going to say. AX plus Y, you just write it straight out. And you see here, you send in Y and X and A, and there is no mention here of any sizes. You see, complex, dimension, unknown. The only thing we need to make sure is that the rank, so this is a rank 1 vector. It's with only, it's a linear vector of rank 1. But we don't know how long it is. We don't have to. This is modern Fortran takes care of this for us. But we need to be careful with the intentions in and in out, because Y is also in and out, since we are doing a reduction type here. So, yeah. So syntax is so easy that it's, yeah. Otherwise, we will have to have a loop and so on. And if we have a loop, then we need to know the size of the vectors and so on. We could query that because there are ways of querying how long is the vector. But it's so easy. So modern Fortran can have vector syntax, and yeah, things become very nice. Then we have this Python program, some imports. I said just n to 3. We make 2 vectors with zeros. Here we need to know the size, because some places we actually need to know the size because this is allocation. So here we have to know how the length of the vector. And as I said before, complex 128 is double precision numbers, and since there are 2 of them in a complex number, their size is 128. And the ordering is Fortran, so it's column major. So the column is the first index. And we fill it with some numbers. The syntax for number they are using 0.1, and this is the numerical value of the imaginary part, and 2.2 for the Y, and then A is just set to 2 and 0.1. So I just to put in some numbers in the complex space. And of course, the question I asked here, how do you know that the Fortran routine uses the same data type? In one of the former lectures, I showed how you can write an agnostic class and module so that Fortran will figure out itself how it was called and what the data types are in the calling sequence. So it will automatically select single, double, or complex data type for you. So you don't have to rely on this S for single, D for double, and C for complex, and Z for double complex that was used for the Fortran 77. It's still common to see that today, but you don't have to do that. You can actually write interfaces and make a class that will fix that for you. So you can just call AX plus Y as I'm doing here. So how do we run this one? We run this one again. C is for the input file, the Fortran file, M for the name of the module. And cross fingers that thing works. The demo effect can be devastating. So we should now have this file here, which is the shared library. Yes, I'll also show you a neat trick that could be interesting to write down. If you use A, you will print out also the name of the library. But this is not, point is that if you are using find combination with grep and such, it's nice to know which file that symbol is actually in. You see here, we have a lot of things that are called, but we are not interested in the called one. We are interested in symbols that are inside our routine. So we call out for the one that is made true. So these are the callable objects, and we are interested in this one. So here is ax plus y underscore, which is typically Fortran. Fortran in most of the implementation appends an underscore on their routines. So if you are programming in C or whatever you like, you need to append the underscore after the name. Normally you don't care, you will just say make a weak symbol. So it still have ax plus y true, and then you will have a symbol called with the W here with the underscore. This is the simplest way. So we can be sure that we can call this function here from the Python program. And we run the Python program. See what happened. It printed out ax plus y, and of course it prints out data before we called ax plus y and after. You see, the x isn't changed. Of course it isn't changed, because if we were to try to change it, if I try to update the x down here, we'll be slapped on our fingers by the teacher, because the compiler is like the teacher. It checked what we are doing. And since we are saying intention in, it's immutable inside here, because this is intention in. So we are not allowed to do any updates on X nor A. They are only intentional in, which means that they are immutable inside the program. Y, on the other hand, it's called in and out. So it has some value when it arrives. Then that value gets updated. And of course, since everything is by reference, then when we copy out and look on Y as a reference, we'll see the updated numbers, which we actually do here. You see both the three numbers are here. So this was a small exercise in complex numbers, and the ax plus y. Ax plus y is a widely used linear algebra operation, so you'll find it everywhere. Of course, this is present in NumPy and so on. So this one you actually don't have to write yourself. So any questions or comments about this demo?
I think people are were typing along with you, Ole. Maybe we could give them some time to finish. If you're finished, or just give a reaction as we mentioned earlier.
Yeah, we can give some time. You see, there is a new question. Yeah, it's going to be fairly more complicated as time progresses today. So not the Fortran or Python thing, but the Unix part. And not everything is set up to be as good, helpful as we like. So no questions. Maybe
If anyone needs time, could you indicate that?
Please indicate if you need time to type along and test it out.
I think everyone is fine. Shall we take a break?
Yeah, I hope you had a good break. Now we are making it slightly harder. We are going to have threaded OpenMP routines. So now we are in the realm of actually doing more fancy computing. We are using OpenMP to make threads for us. OpenMP actually hide all the nasties behind the POSIX threads. No sane person will sit down and write POSIX threads for science. I mean, it's not easy, and it's time consuming and boring. So OpenMP has done it very nicely for us. So we'll use that. We'll use threading in an OpenMP in Fortran. It's supported in C, C++, and Fortran. So I'm using the pi example. Everybody knows that pi is 4 times the arctangent of 1. So you don't have to remember any decimals. Just remember that little expression. And that expression is all. If you do a Taylor series, you can easily get a series expansion, and then you can just take enough elements or sum to smaller and smaller to get the desired accuracy. It's not the most efficient way of calculating pi, but it's a nice one. So this is also another interesting feature with Fortran that we covered before, but it cannot be repeated. If you see, you see here, I have sum. Sum is a reduction variable, so that's fine. It should always be set to 0. But if I declare it up here, set it to 0, it will become 0 here. Next line, if you query sum, it will report 0. So far, so good. If I call this function again, so the function is already called once, it's called into existence, the variables are pushed on the stack and everything is ready for us to run. This part here is not executed again. It's only executed once, which means that when we arrive here, sum has the value it left off here. So sum is not 0, even though I set it to 0 here. This part is only executed the first time we call the function. The rest of the times it's just lying there. This is why you need to be careful to set sum to 0 explicitly here to make 100% sure that sum is 0. Then it's just this function, and of course to be 100% sure that the numbers are the numerical constants are 64-bit reals, you have to underscore it with real 64. Otherwise, you might get warnings and errors that say you need to convert from 32-bit to 64 bits, etc. So it's better just to put it in straight away. So this is the way of saying that that 4 times 0 is the real 64. There are people using D0 in order to use exponent and you signifying double for D, but that's not really good practice. The modern practice is to underscore it with this one, numerical constant like this. So yeah. So this is a single-threaded thing, single-threaded. Then we continue with the OpenMP variable. Again, this one here is the OMP statement. Parallel do, private I don't think it's actually needed because it's smart enough to figure out that the loop counter is private. But this one is important. Reduction, we have a reduction clause. The reduction operation is plus, and the reduction variable is sum. So we don't actually have to do anything. OpenMP will see to that sum are all the sums that end up outside at the end of the loop here. They are all added together. So sum here are the sum of all the sums for all the threads are combined and reduced into this sum here. And we just multiply h with the sum, and we get an estimate for pi. So it's nothing special. This is a very simple OpenMP thing. So I hope it should be fairly easy for everybody to understand. So how do we go again to do this? We will first have to check if this one is present. I'm quite confident it is. Yes, it's there. And there is another issue here. So here is why I put in this variable thing and libraries and such an environment earlier on. For this exercise, we need to set an LD flag because for some reason or another, OpenMP is not specified in the linking part of the build. So, and we can raise the bar a little bit. We introduce some optimization that are fed into the Fortran compiler, both fopenmp, but the thing is that these are optimizing flags. So the fopenmp is not fed into the linker. Of course, the linker still is called gfortran also. It's not LD. So they are linking with linker flags, and the opt flag are not propagated to the linker. So if we omit this one, we'll get an error message. And then the pi again, Fortran code, and the module is called pi. We'll see what happens. Yes, it seems to work. And wrapper functions and so on. What you'll see here is the linking, and there should be somewhere here fopenmp. If we didn't have the flag for a linker, this one would not link the OpenMP library. And we'll get an error. But now it seems to work. So we can set the number of threads to 1. OpenMP always use OMP num threads equals 1. That is normal convention for most program to obey this variable. Sometimes there are other variables, but most of the time OMP num threads will work. And if you specify different variables when you are using Slurm, OMP num threads is the one that it's actually specified or set by Slurm. So we run. This one is a bit time consuming. Maybe it's also need time to start. I saw that it was sluggish to start. Single thread, it took 12.4 seconds. Those of you who find it fashionable or find it nice to know a lot of decimals in pi could probably figure out if there's an error. So you see a single thread used 12.4 seconds, using one thread, 12.8. That within the margin of error because we are not alone on this system. So we can say 2 and run again. We see if we get any speed up. 12 seconds is very long time when you are waiting. 12.4, not too bad. It could be that the OpenMP code for one single thread is actually slower because it has some overhead with the threading library. We see you get nice speed up, almost 2 times. We go to 4. I can't go to more than 4 because I only asked for 4 CPUs. But of course, there are other ways. I could ask for more. Amdahl's law applied to the first one because single thread. Then 3.2. It's almost twice as fast as the 2 threads. So this scales nicely and works nicely. So, any comments or question about this? The only tricky here was the use of environment variables. Well, I introduced this one. Opt. Any options you can give to the compiler can be given as this one. And then the load flag, fopenmp.
Could you just repeat what was this outcome with Fortran, Ole?
With the 4 threads?
Yeah, I'm just want to compare myself.
Yeah. I'm still running on 4 threads. Takes 12.5 seconds to do the single. And it should take 3.2 seconds with 4 threads.
Okay, yeah.
Now, an interesting observation now. This one is what do you think will happen now? Anyone's guess. Remember what I told you about my reservation? In the Slurm reservation, I asked for here, I asked for 4 CPUs per task. Yes, it will now schedule 8 threads on 4 cores. So this is one good thing with Slurm and C groups that it actually encapsulate you. So it should take probably more than 3.2 seconds because they are now running 8 threads on 4 cores. That one first, 2.17. Interesting. because maybe we could do another interesting thing. I always include X. C11. Don't let us a D-1 left running for a long time. It's okay for a short time. You see, now I'm at 100%, which is fine for 12 seconds. So let's see what's happened now when I'm scheduling 8 threads. It actually used 8. So cgroup didn't prevent me from doing more. It should. Huh. When it should prevent me from using more than the threads I had. It don't. So, oh yeah. So be careful how many threads you ask and within your reservation and so on. But you see, the scaling wasn't perfect now. It from going from 4 to 8 didn't give us 1.6. It's 2.2. So I saw there were very little jobs running here, so I'm more or less alone, so it doesn't matter if I overuse. 12, so 2.3. It didn't really help by scheduling more threads because this problem doesn't scale that well. So this is also an interesting observation, the scaling. How does it scale? It scales nicely from 1 to 2 to 4, but apart from that, it don't scale very well. And from 8 to 16, it doesn't scale very well. So scaling is always important to check. So we set it back to 2, so we don't get any problems. So any more comments or questions? We'll see on the no questions here. If one interpretation of the response is that the examples are so good that there are no reason to ask. So, but I'm generally not that lucky, so please go ahead and come with some comments and questions. Okay, maybe we should continue to the number 4 demo. So one last take, questions for the OpenMP Fortran. Okay. No one, nothing on the HackMD. Yeah. Yet. Yeah. Very good. Here I said 4 CPUs per task. You could actually ask for more because there's not that I actually asked for 2 nodes in the reservation. So we should have quite a lot of CPUs to play with. So good. Because I also had it was mentioned in the first readme how to get an interactive one, but then it's good to have it on the collaborative document. Except note that the reservation for Fortran Core runs out or end at 12:15 today. So if you want to run later on with the same, you have to take away the reservation and just wait as a normal user, because I couldn't have the reservation for too long. So that's why it's only valid until 12:15. So yep. Now we are coming into matrix multiplication. And for those of you who took linear algebra, remember that multiplying two matrices by hand, by pencil and paper, is a very time-consuming operation. It grows if you have the n as the size of the vector. It actually the number of computation grows with n to the power of 3. So it grows very rapidly. But the size of the problem only grow with power of 2. And since power of 3 grows much faster than power of 2, we are actually in a very, very good situation. Because we have almost, I won't say unlimited, but in many cases, it feels like we have an unlimited number of compute power of computations. Normal scientific code can only utilize between 3 and 5% of the CPU cycles for computation. The rest, 95% of the time, we are waiting for waiting for data from memory. So as almost all scientific code, I can't say all because somebody will pull up an example that it's not. So I will say most or almost all scientific code are memory bound. We have checked some of them and to document that they actually are, and they all are, that we have tested. There might be some that isn't. Of course, if you write your program, or if the problem you want to solve is so small that it can fit into the cache, then you are in a good situation. But that's a tiny, tiny baby problem, megabyte size. So it's different. So matrix multiplication scales very nicely, and it's an interesting problem because it's well known. Most people know how complicated it is to do by hand. So they are happy to see the computer doing it, and it scales well. So it's widely used. It's the basis of the top 500 test to establish the fastest computers in the world. So you see it a lot. It's always there. So first we need to check if we have this file. Since it's already there, and when I hit enter, it's there. So that's fine. We can do a more on the F90 matrix times matrix multiplication. So there is some tricks up here how to build it. We'll skip that for now. There's an M fill to fill the matrix, which I'm not sure if it's used anymore, but I have the simplest possible way of doing matrix multiplication is A, B, and C, and the N. Here we actually need the N. It could probably have come without it, but since we need the N here for the loops, we can as well just input the N here and you set the dimensions implicit here. So sometimes you could get away with this N, but it doesn't hurt to have it here. I think I have some examples where I omitted the N and use and then had to calculate it here by using the size function and so on. So this is how it's done. 3 loops on top of outside of each other, and it's a fused multiply add instruction. if you were to look on the assembly, we'll see that the fuse multiply add instruction will be used here. So the computer can do it good if given enough optimization leeway to think about the problem and make the best possible code. It can be very efficient. So this is the simple Fortran implementation. But how does it work in Pi? So import matrix multiplication. This is the Fortran stuff. This is NumPy. NumPy is highly optimized. So NumPy is very good. We import time to time this thing. And we say matrix multiplication n equals 400. We fill the matrices with zeros first, and then I fill it with numbers. This is the 0 here is just to make a matrix of this size. Type float, and ordering is Fortran, and I fill it up with 1.1 and 2.2. So you see it's float 64, it's not complex this time. Then I start the timer. I run these 4 loops in Python. I time it again. Print the Z. Python is very nice. If you did this in Fortran, it will be a nightmare because it will fill the screen for minutes to come. Python just skips the between the most of it and just present a few lines automatically. Beauty of Python again. We calculate the sum of the whole thing. NumPy has the sum function built in. Probably a C or Fortran routine back in the behind the scenes. I print out to see if there's some errors and so on. Then we set it to 0 again, and we do A, B, and C, and there's X, Y, Z. And we do the same thing. We call the Fortran routine. We again set it to 0 and initialize it. And we call NumPy. NumPy is highly optimized, so it should be much better than the Fortran code. So we be careful to set the thread to 0 and to 1, so we are sure that NumPy is not using many threads, and that Python is normally only 1 thread, and the Fortran code is not an OpenMP code, so it's only using 1 thread. So all of these should only using 1 thread. You see the Fortran code and the Python code looks very similar. So now we can see the difference in speed. But before we do that, we see that we are still operating on using the GNU Fortran. We can check whether or not optimization have any effect. We've set optimization to just using the defaults. And for the GNU, this is not optimizing at all. Okay, it works. We get an output and there are no error messages, so it should be okay. And we run the thing and see what's happening. Matrix multiplication example. Remember that it was 400 times 400. You can calculate how many, if you could do this in your lifetime. You can sit down and while we are thinking, while this is running, we can think how long would that take to do in manual work. Imagine a piece of paper with 4 by 400 by 400, 16 decimal floating point numbers. Not to mention the probability of doing an error. So I'm running at 100%. We can also spy here. Tanya is also running at 100%. It's also running Python, I would imagine. Yeah. I remember it took quite some time actually to do this, and it's only 400 by 400. It's some time since I ran this last, so I don't really remember how long it actually took. A couple of minutes. Because I'm also not only lazy, but I'm also impatient. Yeah, 180 seconds, which is about 3 minutes. So we should have an answer soon. It's nice to see that people are running. You can see 3 minutes is not really a long time, but when you are watching top, it's it's take quite some time. And top is a very nice utility. So I got 178 seconds, which is close to 180. It's about the same ballpark. My Fortran code clocked in at 0.4 seconds. The NumPy, of course, being highly optimized, C code or Fortran code or a combination of both, are of course beating us tremendously. I mean, this is how it must be, because these codes are highly optimized and matrix multiplication. But you could see just changing the exact same code from Python to Fortran speeded it up from 178 to 0.4. You can divide and see that you get a very high speed up number. So just to make sure that we all agree that, that's not so good. You see the code in Python is like this. In Fortran, it is like this, same code. And of course, you saw that the errors are so small that it's nothing to worry about. They are within what you can expect in this is the numerical precision of a double precision number. So this is within good accuracy. But of course, there is slight difference. This is also important that if you are relying on, let's say, if you have a big ship and want to get the weight of the skipper, you weigh the ship with the skipper and without the skipper, and you subtract the numbers. And when you do that, you are probably out here in the decimals. and you might get the wrong answer because of rounding errors, etc. So be careful when subtracting numbers. So can we do better? Remember, I didn't optimize. So, and it took 0.4 seconds. We try to optimize with O3. It's the simplest optimizer at all. For us, behind the scene, a lot of things going on. So, and did it expand the O3? Yes, here it is. It used O3. So the bad thing here that we have to wait 3 more minutes, but that gives more time to talk and more time to I put the C binding in there since when you are calling C, I've commented out, but if we were to make a class object of this one and a module in C, it's a nice option to give it a C binding number name like this. It's not needed, and if I do it here, it will complain that it's only applicable for modules. But you will quite often put all these routines in a Fortran module, and then you can use this binding to C to show that the C equivalent C number, the C function will be called underscore. So it's not necessarily needed, but if you are using this in a module, you could take away the exclamation mark and then not comment it out, and it will tell the users and tell the system that the actual C name would be mx underscore. So while I'm introducing something that we cannot use in this simple example, it is yet another way of the modern Fortran to integrate nicely and more strict to C, because we now actually expose the correct name that we want to use. So this C function will have this name. So it's not legal to have it outside when there is no module, but within the modules, you can use the binding. So there are integrating C and Fortran contains a lot of new things like binding to make 100% sure that things are the way it should be, and that we can specify how things should be. And if there's a slight disagreement, we will get error messages. So it's to providing us better control over the C interface between C and Fortran. So that's why I had it in there in the first place. Yep. So while we were chatting about that, we now got down to 0.29. And before we had 0.4 or something, 0.4. Not actually doubling performance, but we yanked it down a bit to 2.92, 0.20, well, 0.029. So just using the optimizer gave us far more performance, and there's a lot of optimization flags that we can give. But -03 is generally a good idea to employ on the new compiler. So, can we do better? Yes, we can. We have demos number 5 and number 6. That will actually help us along. We had 180 divided by 4, 3. This is the speed up. This is the speed up from Fortran and Python versus Fortran. So you see it pays off to write your Fortran code. This is a speed up of 6,000. So it's a good idea to use Python code, use Fortran code for the time-consuming parts. But we had to introduce a couple of variables or a bit more strange thing to get things to work before. But now we are actually increasing the complexity a little bit more if we want to do better. We can do better, but it involves more tricks. So do we have the, yeah, this one is present, good. Now we have, you see, I yanked it up to 3,000. I've taken away the Python code because we have already established that it's more efficient. Because we couldn't wait 2 days to get the answer this time. So this time it's only Fortran code. So, but I've also did some other tricks. Not here. Here I used yet another way of dealing with I don't use the ISO environment. I set it myself just to show that you can do it differently. This is the human interface. Precision 6 decimal places, at least 6 decimal places, and at least an exponent plus or minus 20. And then I'm on the real 64. I say at least 15 decimal places and at least 307 range plus minus on the exponent. And then Fortran will come back with a number here. This will report a number. And what that number is actually totally irrelevant because there's no standard what that number should be. It could be 1, 2, 3. It could be anything. So don't rely on the result from here. Quite often this is 8, quite often this is 4, but that's implementation different. So if you come to another compiler, they might give other numbers like 1 and 2 for those integers, and 3 and 4 and 5 or 6 or 7 or anything for the others. So do not rely on the number you get here. So in 32, 8 digits and 16 digits. So this is the human way of setting it instead of just using the computer ways and set aside 32 bits, because you don't really know how that's done in behind the scenes. So this is the human approach. And before you start calculating, you should actually review how many decimals do I need and what's the range of the exponent. But the Fortran code here is exactly the same. So no change here. But we are doing a couple of other interesting things. Here you say, I am changing the module to the Intel module. So Now we are switching compiler from the GNU compiler to the Intel compiler. Hope everything works because we are living in a dynamic environment. So far it's working. And we make the module using the Intel compiler this time. We said set the compiler. You can read the help file and see what it called Intel M. And the rest is the same. Checking out the Intel compiler license and hope that things will work. Warnings. I don't care too much about the warnings. No main. It's depreciated and you use no for main instead. Yeah. Anyway, it's working. We got this library here, and we got what is the compiler doing? It uses O1, optimization 1 here, and is also using QOpenMP because it says OpenMP is standard. So now we can run I think it's 2 now. Just check that we have still 3000, so the numbers can be compared directly. It's reporting that I'm running Python. Also takes some time, this one, because now it's going up from 400 to 3000. But you'll see that we have a normal single-threaded one. So we are not running multiple threads. And you see this one took 35 seconds. So 35 seconds. Can we do better? I think we can. Can we optimize the Fortran code? Yes, we can. We can give it some more options fast. Fast is a good option. We try again. It's propagated the fast. You see, now it's only took 6.3 seconds. So by changing the flag from not from no optimization or just the default optimization. We speeded it up tremendously. You see, this is the first one, no optimization given. And then we gave it fast, and we are down to 6.3 seconds. So this is actually very good. And it's now 10 to 11. We need some break before we embark on the last demo.
Welcome back. Ole, are you ready?
I unmute myself. Yeah, I'm ready.
Yeah, thanks.
So, most of my career, I've been obsessed by getting performance. So, maybe because I'm impatient, but I really think that we will exploit the resource in the best possible way. So, can we do better? Well, we got down to 6.3 seconds from over 30 by just using some optimization. So, more we can do. Yes, there are other flags. We know that we can unroll some loops. That's an old trick in the book. Another more interesting thing is that the processors we have vector instructions with the width of 512 bits. If you divide that up by 4 or by 8, you see how many floating point number it can do in half a clock cycle, actually, in one clock cycle. Every time you turn the crunch, it will take 512 bits and multiply it together, two vectors at that width. So, but the Intel processor have this thing that they get too hot if you are running only AVX 512. So they will normally not use it. They will use 256 instead, not to overheat. But if we are running on a single core, we might be lucky and get less clocking down because of using them. So I put in the optimization flag ZMM. ZMM is for the knowledgeable gurus. It's the register used for the 512 bits. The YMM is for the 256 bit, and the XMM is for the 128 bits. So they are registered using register names depending on the width. And then I use some padding and aligning the loops, and I'm also disabling the check for subscript in range, because if you have to specify an array from 1 to 10 and you try to access the 11th element, that could be dangerous. It could be disastrous. It could abort your program. And so there are often checks that you are not accessing elements outside of this range that you specified. But turning that off saves a little bit performance, gives a little bit more performance, but you make sure that that you don't run over your indexes. You have to have total control over your indexing if you put that on. But this time we do, because the index numbers are fixed. So I'm just locking the door. So the index numbers are fixed, so we are sure that we are not running into any problem. So we go here. I think we need to do like this. Now we are giving the Intel compilers are quite good. I mean, they have been around for a long time. Intel bought a couple of compiler companies many years ago, so they started off with very good, and they do a lot of work to get the performance up. So with all these optimization, could we get better than 6 seconds? 2.9. So from 35 seconds with no optimization or just the default, we could get down to 2.9 with all these special flags. They are okay for matrix multiplication. They might not be always the best, because if these flags were always the best flags, they will be integrated into the OFAST one. OFAST expands to a lot of flags. So I put those one in extra here, and they work nice for matrix multiplication. They might not always work. So instead of relying on using my set of flags here to get peak performance, start off with OFAST and add flag and do some testing, because not the one size doesn't fit all also applies to this one. So now we've done quite well. We managed to get a good performance, and we are close to optimal performance for a single thread. So can we do better? Well, the obvious thing, of course, is to go for an old Emacs file lying around, RM. Of course, we can go for more optimization by means of having more threads.
Can I interrupt you?
Yeah.
There is a question, number 3. Could you answer that?
Yeah. It's hard. It by default is GNU. If you don't give any Fortran compiler, it will use GNU. So yeah. So that's the default is the GNU compiler. So what we are trying to do now is to actually invoke the math kernel library. Of course, matrix multiplication is the simple thing, but math kernel library contains a huge range of libraries that you can call up. So in being able to exploit all the nice features and nice libraries contained in the math kernel library is good. But as you see already on the screen, it takes a lot of strange things to do so, unfortunately. It's not really set up easy to do. And I'm also introducing the LD preload. LD preload is dangerous. It is to be avoided if you can, and never ever put it in the bash file, because it's a powerful tool, but you don't know. It's like having a gun that you don't know where it's aiming. It would aim straight in your face, because it's like having a gun where you cannot control the aiming. So it can be quite dangerous to use, but if you are using it in a script, it's fairly safe, because when the script is done, then the preload library, the preload variable is not set anymore. So the point is now that we want to use an Intel library and Fortran OpenMP code to do matrix multiplication. So there's a lot of strange things, and we'll take them one by one. But first, we can take a look on the Python code. Now we are yanked it up to 1 to 10,000. Here I call the MXM, which is my Fortran code. Then I call my Fortran code, but another different one, called with mlib, which is the Fortran code calling the MKL library. And then we are comparing it to the highly optimized matrix multiplication, which should be they should be fairly equal to the MKL. But there would be difference. I wouldn't be really surprised if the NumPy was even better than MKL, because it's less overhead calling the NumPy directly than calling the MKL. So it's interesting to see. So the Fortran code, forget the MFIL. Here we have the matrix multiplication again, same code. The only thing I did here was to introduce the parallel OpenMP parallel. I expect that the majority of you are fairly well acquainted with OpenMP. So it's easy there is no reduction and so on. Of course, there is reduction because, well, accumulation here, C equals C plus some extra. So it's an accumulation. But it's one element, so it's safe, it's thread safe. Should be okay. And then we can have many threads on the simple Fortran code. And we can call up the library. The only thing that happened here is that I'm calling the D. And of course, this is now we are on the back to the 1970s, 1980s type standard, where you have to put a letter at the first one here, a prefix letter to tell the size of the variables. It's a D for double precision. If you use S, it will be single precision, and of course C and Z for the corresponding complex parts. So we have to go to review this code here. First, we will check if this is here. Yes, good. Then we set an export flag. Now we are using a single thread for the MKL. Then we export the preload. First of all, we can see what is the MKL root. That's set by the module. This module here is doing it nice for us. It says MKL, which is this one. So don't really bother with thinking what this is. Just use the MKL root because it's set for us. We set the load, the variable. The preload is actually loading the libraries before the executable is launched. So if the executable are asking for libraries, they are already loaded up before the executable is starting to execute. And you can do all sorts of tricks with the preload, but if you screw up, nothing will work. So, and then that's the dangerous to have it in your bash shell. If you do it wrong there, you are unable to log in. So be careful. Then you have to have some help from the admin to help you out. So do not use LD preload in your bash script. Many times you type ls and it won't work and so on, and because bin-ls won't work because the preload library is wrong and so on, and yeah. So preload is a magic wand for some time, but it's also a loose cannon on deck, so it could be dangerous, as I said before. Right. So what does it expand to? You see, I've also used something here with the directory name, which and so on, and in order to get the hold of the Intel 64 OpenMP library. which you can see it expanded this long, strange path. Anyway, we now have the LD preload set up. What more do we need to do? Some flags needs to be set. We run again and running on a single core. I'm always surprised that this worked. It took me quite some time to figure this out. So this is really to be on the edge side. So now we can say Python mxm.3. And remember, I also yanked up the size to 10,000. So what's happened here? You see resident is 1.6 gig. It's not that big. So and you can see we are running on a single core with a footprint of 1.7. It should be slightly higher. You remember 1.7 gig was a lot. Now it's nothing. For reference, if you have 32-bit system, the maximum you can use is 2. In principle, you could reach 4 if you use an unsigned integer, but the addresses there are some limitations. So normally you can only reach 2 gigabyte with the 32-bit. So it's slowly increasing to about 2 gig of footprint. But we are running on a single core, so it will take some time. But of course, the exercise here is to run with a multiple number of threads later on. So we'll see how much better we can do. So the first iteration here will be the most time consuming. HTOP was not installed on this system. Okay. Somebody is running with more threads, which is a good thing. So the Fortran code did it in 106 seconds. The math kernel library in 45. So it's only 2 times faster. And NumPy now is running NumPy. NumPy might be slightly faster because it's has less overhead, not calling Fortran routines and so on. First of all, they are calling my Fortran routine. Then my Fortran routine is calling the MKL. And then that introduces slight overhead. And I'm also suspecting that the NumPy people, since NumPy is so much used, have gone to the length of having it performing better, slightly better, but it's not really significant compared to what we had before. So we arrived at 106 seconds on normal Fortran code and 45, around 40 to 45 for the highly optimized libraries. So now we can do it in parallel. we said unset the LD flags. We set the number of cores to 4. We tried this little trick here. Should be okay. A lot of strange flags, but hopefully we'll get things to run. OpenMP is included. So now, I set number of threads to 4. And we try to run 10,000 again. 397. It's not 100% perfect, but we arrive at, it should be, it took the 106 seconds or something thereabout. So it should clock in at 25. You see the time is spent is CPU time. So now it's doing 4 times the real time. So the Fortran code clocked in at 26, which is nice. 27, which is about 4 times faster. The MKL clocked in at 11, about 4 times. NumPy, matrix multiply, clocked in at 10. It's about 4 times faster than last time. So scaling seems to be okay. Since there are no limitations on what I could do, I could say 16 and run again. I only get 8. Okay, I only get 8. And maybe I'm running 2 threads per core also, so that shouldn't really make it much faster. 21. It's comparable to what we had. So now we run with 2 threads per core. We actually got some gain. With 2 threads per core, we actually got a little bit of gain. Interesting. But you see, it's scale. So if you had requested more, if I had requested more cores to run on, I could have get even higher performance. So, is there anything more we can do? I think we have more or less reached the end of what we can do here. So we can get it down to 20 seconds for the 10,000. And remember, we started at a very high number with 3,000. So, of course, you could put in CPUs per task 16. And if I issue this one here, I have to log out on that node. See if I can say 16. I'm in. I'm actually in. Demo 6. We LD flags we didn't need, but we need to do this one. Ah, yes, of course. Here you saw the problem with LD preload again. I'm lucky to manage to gain control. I think I asked for 16. I can try with 8 first. Aha. What did we do wrong here? So why isn't it giving us the... It complains about the math kernel library. So didn't I read my own README correctly? The LD preload. It seems okay. Mm. It worked here. So something is not right. Why not do it here? So we got the same thing here. Now we are in an interesting situation. But I also got it here. We build it once again. So if you follow the README instructions, it will be okay. Now they are both at 8, I think. So $20. Remember that is the simple Fortran code. It's not optimized at all. It's the plain 3 loops outside each other, plain code that takes only twice the amount of time that the library can do. So it must be said that for this matrix multiplication here, the Intel compiler are extremely good. I've never seen any compiler come close to it. It's just like magically it understands what's going on here. I think they've done a lot of work in order to recognize that this is a matrix multiplication. So we get this 13 seconds. This goes down to 5. You see the MKL library scales better. Echo 8. So maybe we should try to set it to 16 and see if we can get how well it scales. We got our Fortran code down to 13 and the library at 5. My Fortran code at 6, the library at 2, 2.5. So you could see with the libraries, you get it down to 2.8, but the standard Fortran code, no matrix multiplication in real life would do it as simple as that. It will be done with a lot of padding or tiling, a lot of tricks that will be done. But the compiler actually recognized that kind of code so that it's only 2 times slower than the library. So we are actually, and it scales reasonably well. So we are actually in a quite good position now to solve mathematical problems of any kind from within Python. And that was most of that covered what I had planned to say today. So